So, continuing with our discussion for the dynamics of rotational motion about the fixed axis, where we dealt in torque, etc. Now we take up angular momentum and L and its conservation, etc. Okay, so we have again the same constraints, that is, the rotation is about a fixed axis, and in which case we define L for a given particle as a system of particles, the body that we have rotating about a fixed axis, that the angular momentum L is equal to summation of Ri cross Pi. So we know that for a typical particle, the angular momentum is defined as L is equal to R cross P. But like I discussed the other day, the origin is over here, O, and we defined R like this. This is the diagram from the last, the spillover of the last lecture, and there we can see that this vector R is the sum of two vectors. One is OC and the other is CP. They are also the length vectors which make up the vector R according to the law of addition of vectors. So then we have here another definition, and that is the definition of linear momentum P, which is equal to m v, where both the vectors P and V are in the same direction parallel to each other. Now if we substitute that here, then I get L is equal to OC cross MV plus CP, OC cross MV plus CP cross MV, where the magnitude of the vector V is equal to V is given as omega R. Of course, this vector V is tangential at P to the circle in which this motion is taking place about this fixed axis, which we have taken as the Z axis. Okay, so CP cross MV is parallel to the fixed axis. We have to use the right hand curl rule, and it turns out that because this is in the plane perpendicular to the Z axis, the circular motion, therefore it turns out to be parallel to the fixed axis, which is the Z axis, R indicated by K cap. So I can write for the first part here, CP cross MV is equal to R perpendicular, the perpendicular part of it, into MV K cap, where R perpendicular, M and V, they are scalars. And as I substitute for V here as omega R perpendicular, so I get, rearranging terms, M R perpendicular square omega into K cap. So we found for the CP part that CP cross MV is equal to M R perpendicular square omega K cap. Okay, and now similarly we can see that OC is like this. cross V, that is in a plane, and this we find that this is perpendicular to the fixed axis. This is perpendicular to the fixed axis. When we rotate by the right hand, the first vector towards the second vector, we find the direction. That direction turns out to be perpendicular to the fixed axis. Now, if I write this L in two components, and if I say that Lz is a part of a component of L, the angular momentum, along the z axis. Okay, the other part will say that this is a perpendicular part. So I can write Lz, that part of L along the z axis, which we define as Cp into mv, which we obtain r square omega k cap. So L is equal to Lz, this component plus the other component, OC cross mv. Okay. Now, so the value of L is defined as Lz plus this part. Note, we must note that Lz is parallel to the z axis. Lz is parallel to the z axis, but L is not. That is, their direction, their senses could be different. In general, the angular momentum and the angular velocity omega are not necessarily parallel. I repeat, in general, the angular momentum and the angular velocity are not necessarily parallel. And if we compare that to the case of translatory motion, then we find that P, the linear momentum, and V, the linear velocity, are always parallel to each other by definition also, because P is equal to mv. Okay. So now let us write the total angular momentum of the system, and we define it as L is equal to the summation from I to N for the various particles, and for the corresponding Li, and which I can write in two parts. One part is Liz, the z component of Li, plus OCI into MIVI. The second part, which we have here from this relation, I substitute there, and we obtain the total angular momentum of the system. We can calculate for all the particles comprising the rigid body. Here I can say that let L be two parts. One is the part perpendicular to the z axis, and the other is the part which is along the z axis. The two parts, L perpendicular and Lz. So, using the various definitions, I had written L as two parts. One was L perpendicular and the other was L along the axis of the rotation. So I can write it again as L perpendicular is equal to summation OCI corresponding to the ith particle cross mv. Okay, and Lz I can write as summation Liz over the entire range of particles, which I can write as summation m1 Ri square into omega. What is this? This is the moment of inertia of the particles, moment of inertia of the body, multiplied by omega, which is the angular velocity, And of course all these terms here are scalars into k cap, which shows the direction vector. Or I can write this equation simply as I omega k cap. Okay, so I can write L again as Lz plus L perpendicular. Okay, but we have to see that the rigid bodies that we are considering over here are symmetric about the axis of rotation. I'm just writing a short form for the axis of rotation, which means that the axis of rotation is one of the symmetry axes of the body under consideration. Now, bear in mind that for OCI, O was here, CI is here in the diagram, the other diagram that you have. For a given OCI, for every particle which has a velocity Vi plus Vi, there is another particle of velocity minus Vi. And these two particles, as I have just shown in the schematics over here, they are at the opposite ends of a diameter of the circle of which the center is Ci. So this I have shown to have positive velocity here, and this I have shown negative velocity here, and the effect is that the contribution of these two cancel out each other. So we had seen that particles moving in the circuit, for the diametrically opposite pairs, their contribution to the perpendicular component of the torque is equal to 0. So I can write in that equation that the perpendicular component of the torque is equal to 0, which leaves us with the total torque, the total angular momentum is equal to the angular momentum along the z-axis, which is I omega into k cap. Okay. Now that was about the body which is symmetrical about the axis of rotation. For bodies not symmetrical about the axis of rotation, this component Lz is not equal to L. For those which are symmetric, Lz is equal to L. So I can write from here again that Lz is equal to I omega, where this is the moment of inertia into the angular velocity, k cap, and when I differentiate with respect to t, the time, I get ddt of Lz is equal to ddt of I omega into k cap. And dl dt is defined as torque from before. Now, we have to recall that only components of the torque along the axis of rotation need to be accounted for. Those perpendicular to it are not to be accounted for. And therefore I can write a very simple equation that my vector torque is equal to the magnitude torque into k cap, which establishes that the direction of the torque is the same as the axis of rotation. Now, there was a definition that L is equal to Lz plus L perpendicular, and as k is fixed, the direction of k is z-axis, it cannot change, it is invariant, so I can just write that dLz upon dt equal to torque into k cap, and dl perpendicular upon dt is equal to 0. So for rotation about fixed axis, since it is equal to 0, it means that L perpendicular is the constant. Okay. Now as Lz, the component along the z-axis, the axis of rotation is equal to I omega into k cap that we have obtained before. So I can write that ddt of I omega is equal to torque. Of course, because there is only one direction, therefore we will not consider this as a vector, but we are considering it as a scalar equation. So if our moment of inertia is not a function of time, it is time independent, then in the relation that we defined there, then ddt of I omega, I will come out and this will turn out to be equal to I d omega over dt, and d omega over dt is defined as alpha. Okay, so what I get is that my torque is equal to I alpha. Just like in the case of force, this was equal to m into a. So taking a complete analogy, in this situation of the angular momentum and torque relations, we get the torque is equal to moment of inertia into alpha, the angular acceleration. Now, like in the case of the conservation of the linear momentum, we can consider the conservation of angular momentum. And if the external torque, there the external force was equal to 0, here we are taking the external torque to be equal to 0. If it is so, then Lz, which is also equal to L normally for symmetric bodies, okay, so this is equal to I omega is equal to a constant. So I am writing that here, that because Lz and L are the same, one and the same, therefore we say that the angular momentum of the system is equal to the moment of inertia multiplied by the angular velocity, which is equal to a constant. Which means that if somehow in this given situation I increase the value of I, the value of omega will go down. And if otherwise the value of I is decreased, the value of omega will go up, which is what is in the circus acrobats, they use this situation. Or maybe you are sitting in a chair and this chair is rotated fast, but then what you do, you extend your hands and the moment of inertia is increased so that your angular velocity decreases. There are many examples of that which you can look in the books. Now I am just going to tell you that the relation between I and omega, which is given here, can be described with the help of an xy curve. I can take omega over here, or alternately I can take I on the y-axis and omega here on the x-axis. In both the cases, I get a curve of inverse proportionality. The beauty of this curve is that for every point on this curve, if I draw like I have drawn here, I get a rectangle here and I get a rectangle here, and I1 omega 1 is equal to I2 omega 2, therefore the areas which are covered by these are the same. Of course, these approach infinity. In the y is proportional to x, y is equal to k into 1 upon x. If y is plotted against x, then we get a graph which asymptotically reaches 0 here and infinity over here. Okay. There is a similar graph, and that graph is e to the power of minus t or tau. In the decay problems, in chemistry you must have seen decay problems, and deal that decay problem also in physics, in not the decay but the discharge of capacitors, etc., where we will get a relation of the kind e raised to the power of minus t upon tau. Now tell me, the only thing we understand is T has got the dimension of time. So this tau here has also got the dimensions of time, so that the power of E is a pure number. And E itself is a pure number. We will have occasion to describe this Euler's number later on. Now, what we have done today is we have talked about the rotational motion about a fixed axis, and we have talked about angular momentum and the various attributes of the angular momentum. We have also seen that the angular momentum and the angular velocity need not be in the same direction. For a fixed axis, of course, that is there, but we have seen that, not like in the case of the translatory motion, where P and V have got the same direction necessarily, always, without fail. Okay, next item that we are going to have in the next lecture, I am going to talk to you about the rolling motion and the kinetic energy of rotation, etc., and how it is conserved with the help of examples. So that will, in the next lecture, will bring to a close of the what we call the mechanics of the rotation of a system of particles, and we then probe into gravitation, which is easy. One thing I would like to tell you, these set of derivations are very tricky. If this, then that, take it from here, recall this, that, you ought to do is several times in your preparation for your examinations, and maybe 4 or 5 times will help you. Okay, the average student. Of course, the bright ones I'm not talking about, and I'm not addressing them. In the end, I would like again your attention to this queries and answers, which you can put in the comment section, and I hope you do that, and I will enjoy by addressing those concerns of yours maybe in the near future. So, thank you very much.